Hassan, do you have my voice? Mr. Ghassan Al-Hasnawi, do you have my voice? Okay. In the previous session, we see this definition: an operator T in B of H. H is a Hilbert space. Is said to be self-adjoint or Hermitian if T equal to the adjoint of T. A slightly larger class of operators, which is the correct class of operators for the purpose of this spectral theorem, is dealt with in our next definition. This definition: an operator Z is said to be normal if we have this equality: Z star Z equal to Z Z star, and Z star is the adjoint of Z. Okay. And also we see this proposition: let Z be in B of H. Z is normal if and only if the norm of Z of X equal to the norm of Z star of X for any X in H. And if Z is normal, then we have this equality. More generally, we have these equalities for each natural numbers n, and consequently the spectrum of Z equal to the norm of Z. And we see the proof of this proposition in the previous session. Now we have this proposition: let X belong to B of H is a self-adjoint and P be an polynomial with variable T and with complex coefficients. Then the norm of P of X equal to the norm of this polynomial in this set. The definition of this norm is this: the supremum of P of T for any T in sigma of X. Please note that P is a polynomial. So, for example, if you consider P in C of T, then there exists, for example, alpha 1, alpha n in complex numbers such that finally this proposition equal to alpha 1 plus alpha 2, or we can say alpha alpha 0 plus there exists alpha 0, alpha 1. This is equal to alpha 0 plus alpha 1 t, and so that this is equal to alpha 0 plus alpha x. plus alpha 1 alpha 2 x2 and finally alpha n xn. So that this is an operator. This is an operator from H to H. Now the norm of this bounded operator from H to H equal to this supremum, and we denoted this supremum by this norm. Okay. Proof. Notice that Q equal to the absolute value of P to the power of 2, and this is equal to P bar multiplied by P. And since P is a polynomial, Q is a polynomial too, and we know that the coefficient of this polynomial are real because this is real, okay, and hence Q of X is self-adjoint, because if for example if Q of X equal to okay, we have a problem in this work. Okay, it is very trivial that Q of X is self-adjoint because we assume that X is a self-adjoint operator, okay? So X star equal to X, and if we can write in this, for example, if Q of equal to one, and this is equal to the conjugate of this constant equal to itself, because this is real, and this is equal to the conjugate of B1, the conjugate of B1 multiplied by X star, and finally the conjugate of Bn multiplied by x star to the power of m, but x star equal to x, so that this is equal to b0 plus b1 x plus bm xm, and it is equal to q of x, so that this operator is self-adjoint. It is from proposition 156 part 2 and the spectral mapping theorem. We see that the norm of this operator to the power of 2 equal to the norm of this. We see this, and this is equal to this, and this equal to this, because p bar multiplied by p equal to q, and this is equal to the supremum by the spectral mapping theorem, and this is equal to all q of t such that t belongs to sigma of x, and this is equal to this norm by our definition. This is our definition, okay, by this definition, and this is equal to this norm to the power of 2, and the proof of this proposition is complete. Just as very complex number has a unique decomposition into real and imaginary part, it is seen that each z in B of h has a unique Cartesian decomposition, such as this: z equal to x plus I y, with x and y being self-adjoint operator, and it is trivial because if we have this equality, we know that x equal to this and y equal to this. So in fact x, the inner product of x and x, let me know this both. Okay. For any x in H, this inner product x and x equal to this operator of x and x, okay? Z plus Z star, Z plus Z star of x and x, and this is equal to 1 divided by 2 Z of x and x plus Z star of x and x, okay? and we know that this is the conjugate of this. So this is equal to zx and x plus zx and x conjugate. And this is equal to the real of this complex number, okay? Real of zx and x. Because for any complex number we know that, for example, z plus z bar equal to 2 real of z, okay? And also for any x in x, yx and x equal to the image of this. So by this definition we can form this x and y, and these two operators are self-adjoint because this is real function. For this reason we sometimes write x equal to the real of z and y equal to the image of z. For further reference we make some observation on the Cartesian decomposition of a normal operator, and we have this proposition in normal operator. Mr. Kassan, do you have my voice? Mr. Hassan Al-Hasnawi, do you have my voice? Okay. Let z be equal to x plus iy, and this is the Cartesian decomposition of an operator. Then the following conditions are equivalent. Z is normal for any x in H, zx to the power of 2 equal to xx plus yx, and xy equal to yx. This x and y commute with each other. First, notice that for z equal to x plus iy, we have this norm equal to this norm, and this is equal to the norm of first, the norm of second, and minus 2 real of this. While the norm of z star of x equal to this, so that these two are the same if and only if this equal to 0, and this is equal to 0 if and only if we have this equality. Notice finally that the real of this is equal to 0 if and only if this be a real number, and that since x and y are self-adjoint, this inner product belong to R if and only if we have this equality. So this proposition is very easy, and in this section we have approximate eigenvalue definition. A scalar lambda is said to be approximate eigenvalue of an operator z if there exists a sequence xn such that this limit equal to 0, so that this scalar is said to be an approximate eigenvalue of an operator Z if there exists a sequence such that we have this relation, this limit b equal to 0. In eigenvalue, you know that we must have an element such as x such that z minus lambda x equal to 0, but in approximate eigenvalue we must have a sequence such that this limit equal to 0. Here and in the sequel we shall employ the symbol S of h to denote the unit sphere of h. Thus f of h, S of h equal to the set of all x in h such that the norm of x equal to 1. And we have this theorem. Suppose z belongs to b of h. Suppose z in b of h is normal, then z belongs to gl of h. gl of h is the set of all elements in h that are invertible. The set of all invertible elements in h. Z is invertible if and only if z is bounded below by this definition. There is an epsilon positive such that we have this relation for any x. Z of x is greater or equal epsilon x. Equivalently, the infimum of z of x such that x belongs to S of h must be greater or equal epsilon, and this is non-zero, so that this infimum is non-zero. Okay, and this is very trivial because if we have this relation z of x greater or equal epsilon multiplied by the norm of x, for each x in h, z of x is greater or equal epsilon this. Okay, this is equal to, for any non-zero elements in h, the norm of this vector greater or equal epsilon. We divided two sides of this inequality by the norm of x, and the norm of x can be moved into this norm and can be write such as this because there is a linear function, and this is equal to, for any y in S of h, norm of z of y is greater or equal epsilon, because we can consider y equal to x divided by this. Okay, all of these are in S of h, and this shows that the infimum of this set must be greater or equal epsilon. Is equal to the infimum of this set z of y such that y belong to S of H is greater or equal epsilon. And 2, so that these two are equivalent, okay? Lambda belongs to sigma of Z if and only if lambda is an approximate eigenvalue of Z. From 1, we see that if Z is invertible, if Z belongs to GL of H, then for any x in H, the norm of x equal to this norm, Z minus 1, Zx. And this is less than or equal the norm of this multiplied by the norm of Z of x, which shows that the norm of Z of x is greater or equal x divided by this norm. And so we found a C or epsilon, if we consider this as or epsilon, the inverse of this norm. We have this inequality. So Z is bounded below. So S is bounded below. And okay. If conversely Z is bounded below, deduce two consequences such as this. Z star also bounded below. By this proposition, we can see this, and hence the kernel of Z star equal to 0, because if Z star is bounded below, we have this relation that if Z star is bounded below, this infimum must be positive. Now let we have a non-zero element in this kernel. If let x be non-zero and be in kernel of Z, then x divided by the norm of x also is an element of the kernel of Z. So Z of this equal to 0. Therefore, this infimum must be equal to 0. The norm of Z, y for example, such that y belongs to S of H. Because if one of these elements equal to 0, this infimum equal to 0. We found an element in S of H such that this is equal to 0, so that this is equal to 0. And this is a contradiction because this infimum must be positive. If Z be bounded below, this infimum must be positive. We prove this infimum must be positive. So that any non-zero element cannot be in the kernel of Z. So the kernel of Z must be equal to 0 only. This shows that the range of Z is dense in H by part 3 of proposition 152. Please follow this. And B, Z has a closed range. For this reason, if we have a sequence that Z of Xn belongs to Y, please note that we know that in any metric space, X is an element of the closure of A if and only if there exists a limit in A such that the limit of Xn equal to X. Okay. Now let X belong to the image of Z bar. This shows that there exists a net or sequence in Z of H. We consider Z in a set of A such that the limit of Yn equal to this X. Okay, and for each n, Yn is an element of Z of H, so that Yn is Z of 1xn. This shows that there exists a sequence xn in H such that Yn equal to Z of xn, and we have this relation. Limit of Z of xn equal to X. Okay. This shows that Xn must be Cauchy sequence and so must have an limit shows that is xn Cauchy sequence and so that because H is complete, there exists, for example, y0 in H such that the limit of xn equal to y0, okay? And this shows that x equal to the limit of yn, and yn is z of xn. This is equal to the limit of z of xn, and this is equal to z of the limit of xn, and the limit of xn equal to y0. Z of y0 is an element of z of h. Z of y0 is an element of z of h. This shows that any element of this closure is an element of itself. So z of h bar is a subset of z of h, and this shows that z of h bar is equal to, because we know that always z of h is a subset of z of h bar, and this shows that z of h is closed. Is closed. Did you note that? We have this and we have this. A equal to a bar if and only if A is closed. A is closed. So that Z has a closed range, and also Z star is also bounded below. From A and B, you conclude that Z is a bijective linear map of H into itself and hence invertible. Okay. Note first, note first that Z minus lambda inherits normality from Z. If Z, since Z is normal, this is a normal operator. Then deduce from 1 that lambda is an element of sigma of Z if and only if there exists a sequence in S of H such that we have this relation. All Z of xn tend to lambda. So lambda is an approximate eigenvalue of Z. And this is a very nice proposition, and we have this corollary x equal to x star if and only if the sigma of x is be real. Proof: if there exists a sequence xn in S of h satisfying the condition is not equal to 0, then also we have this. Okay, and hence lambda equal to this and this equal to this limit, and this limit is a real number because we know that all of these are real. For later reference, we will record an immediate consequence of theorem 162. Corollary: suppose lambda equal to alpha plus I beta and z equal to x plus I bar. So this is a self-adjoint decomposition of z, and this is the representation of this complex number, or the Cartesian decomposition of S calis, lambda and normal operator z respectively. Then the following conditions are equivalent: lambda belongs to sigma of z. 2. There exists a sequence xn such that this norm tend to this norm converges to 0, and also this converges to 0. And we have important classes of operator. Remark: the operator P in B of H constructed in theorem 1,430 is referred to as orthogonal projection. Please see this: orthogonal projection 1,430. Let me review this. Any vector x in Hilbert space can be uniquely expressed in the form x equal to y plus z, where y is belong to M and z belong to the vertical of M. And for this, if x, y and z are as in 3 above, then the equation P of x equal to y, we define P of any element. This is an arbitrary element, okay? We map this x to this part, to y. This is a bounded operator. P belongs to B of H, and this P have this property. Okay? Discover the projection on okay. Discover orthogonal projection onto the closed subspace M. When it is necessary to indicate the relation between the subspace M and the projection P, we will write P equal to Pm and M equal to the range of P. Note that M is indeed the range of the operator P. Some other facts about closed subspaces and projections are spelled out in the following exercises. This exercise is very important properties for projections. Please write this exercise as your homework, okay? As your homework. Okay. Please solve these exercises as homework. Do you understand? Mr. Qassam, Muhammad Al-Khafaji, do you understand? Okay. And we have this proposition. Let P belong to B of X, then the following two conditions are equivalent. P equal to Pm is the orthogonal projection onto some closed subspace M, and P equal to P2 equal to P star. And the proof of this is very easy. For example, I plus 2, if P equal to Pm, the definition of an orthogonal projection shows that P equal to P2, because, for example, if you know that P of X equal to Y, if X equal to Y plus Z such that Y belong to M and Z belong to the vertical of M, then P of X equal to Y. This shows that P2 of X or P of X equal to P of Y, because P of X equal to Y, and this is equal to, we want to prove that these two are the same. This is equal to P of Y plus P of X, and this is equal to, because this is equal to 0, okay? The kernel of, sorry, this is Z. Z is in the kernel of P is equal to Z. Okay, let me and this is equal to P of X, P of Y plus Z, and this is equal to P of X. This holds for any X, and so P2 equal to P, and also P star equal to P, and the self-adjointness of P follows from this, because P equal to P star, okay? And 2 implies 1, suppose 2 is satisfied, let M equal to the range of P, and denote that X belong to M. If X belong to M, then there exists Y in S such that we have this equality. It shows that P of X equal to P2 of Y, and this is equal to P of Y, this is equal to X. On the other hand, note that Y belong to the vertical of M if and only if we have this statement for each Z. The inner product of Y and P of Z must be equal to 0, and this is equal to this because P star equal to P, and this is equal to P of Y must be equal to 0, so that Y must be belong to the kernel of P. Hence, if Z belong to X and X be the image of Z under Pn, Y equal to this, we find this equation. Okay, so we see that these two are equivalent. We have the operator matrices. If Mn be a sequence of pairwise orthogonal closed subspace, and if M equal to the subspace generate by this union, we know that if we take the union of some subset, this union may be not a subset, but we can construct the smallest subspace containing this union. We say that M is the direct sum of the closed subspaces Mi, and we write M equal to this, so that this M denoted by this, the smallest sigma algebra containing this union, I the sigma algebra generated by this union. Conversely, whenever we use the above symbol, it will always be tactily assume that the MIs are closed subspaces which are pairwise orthogonal, and that M is the closed subspace spanned by them. Okay. For matrices, if we suppose S equal to H1 direct sum by H2, this is the definition of a countable number of subspace. We consider two only, okay? We shall think of a typical element X as a Coulomb vector X equal to X1 and X2 with Xi belong to Hi. Let Pi equal to the projection on Hi. So Pi of X equal to Xi in the above notation, okay? If we think of Pi as being an element of B of H and Hi, then it is easily seen that its adjoint is the isometric element Vi of B of Hi and H. The script thus V1 of X1 equal to this and V2 of X2 equal to this. Given a T in B of H, given Tij equal to Pi T Vi. And observe that we have this relation T of X equal to this matrix product Please note that we have this notations. Pi is this projection map, and Vi of x1 equal to this and V2 is equal to this. So we know Pi and Vj, and this is Tij. If we refer to Tij as a matrix corresponding to T, then the matrices corresponding to P1 and P2 are seem to be this and this. Okay. And also we have this section, isometric versus unitary. The two propositions given below identify two important classes of operators between Hilbert spaces. Proposition let H and K be Hilbert spaces. The following condition on an operator U in B of H and K are equivalent. If this is any orthogonal set in H, then also U of EI is an orthogonal set in K. So the image of any orthonormal set is orthonormal set. But this is a subset of H, but the image of this under U is a subset of K. There is an orthonormal base EI for H such that U of EI is an orthonormal set in K, and we have this relation. These three statements are equivalent. And also for any x, the norm of U of x equal to x and U star U equal to the identity map on H. An operator satisfying this equivalent condition is called isometry. This is very important. This is the definition of an isometry in Hilbert spaces. And the proof of this is very easy. Please read the proof of this from the book, and also this proposition 17 why 176 and example 177. Let me write for you. Do you, okay. Muhammad, do you understand? It is clear? Okay. Because this proof is straightforward, and we have this definition: two operators T and S, T in B of H and S in B of K, are said unitarily equivalent if there exists a unitary operator U another from this and this in U of H and K, such that we have this relation S equal to U T U star. Okay, please read the rest of this chapter. We will continue in the next session by this chapter. Mr. Qasan and Muhammad, do you have any question? Do you have any question? Okay. We continue tomorrow, inshallah. Thank you for attention and goodbye for now. Goodbye.